In the last section, we were looking at titrations. We said that a titration was used to determine the concentration of an unknown solution, and that we use an indicator to tell us when the reaction is done. Well, how do we choose our indicator? Now, when we look at different types of indicators, it turns out that most of our indicators are actually weak acids themselves. Because they're weak acids, they exist in equilibrium, and so the reaction can go both ways. So my indicator, when it's a weak acid, will have one color. When it breaks apart into the conjugate base and a proton, it will have another color. Okay? Now we want to choose an indicator that's going to change colors at about the same point as our equivalence point. Now if we look at the first reaction, phenolphthalein will turn just a little bit of pink right here at this line. It's kind of hard to see, but it's about when it starts changing colors. So it'll fall within here. Methyl red starts changing colors down here, so it's not going to be that great. So I would probably want to choose phenolphthalein because this falls within its color change. Same thing here. My equivalence point up here is about here, so I'm going to want to choose phenolphthalein because I'm going to have that color change there. Now, I can sometimes be given a table that tells me when things are changing colors. So I know that a strong acid and a strong base are going to reach equivalence point at about 7. So I would want an indicator that changes color at about 7. So if I look here, I would actually probably choose phenol red because it's going to start changing colors at about 7. Now if you notice, none of these start changing at exactly 7. That's why we call our color change the end point. It isn't the true equivalence point. My H plus and my OH negative aren't exactly equal, but it's going to be close. I know that if I have a weak acid and a strong base, the equivalence point is going to be greater than 7. So I would want to choose an indicator that's going to change colors greater than 7. I could probably choose phenolphthalein, I could probably choose thymol blue, because both of those are going to change colors greater than 7. Now, when I choose an indicator, because my indicators are weak acid, the color change is going to be determined by their pKa value. Remember, the pKa is the negative log of their Ka value. And what I want when I look at Ka values, the pH where I want my color change to occur is going to be equal to the pKa minus 1. There's a whole big long algebraic expression that explains why, but all you need to know is if you're given the pKa values or the Ka values, you determine the pKa minus 1. That'll tell you where it's going to change color. Okay? So everything we've looked at up until this point has been equilibrium with acids and bases. But we can also have equilibrium that's going to involve precipitates. So this should look pretty familiar. These are our solubility rules from way back in chapter 4. And what this is telling us is whether or not a precipitate is likely to form. So anything with a nitrate or an acetate, not going to form a precipitate. Chloride ions, bromide ions, iodide ions, usually soluble, except if they're partnered up with silver, mercury, or lead. So these kind of tell us what's going to happen. If I have a precipitate form, anytime I've got a precipitate, I've got equilibrium. And the reason I have equilibrium is some of my solid in solution is going to break apart to form the ions. Now, not a lot, but some. The amount that my solid will break apart is going to be represented by my KSP. It's still a K, so it represents equilibrium. It's a constant. SP stands for solubility product. Okay? Now, just like every other K value, it's the concentration of our products. In this case, it would be Ag plus and Cl minus raised to their coefficients over the reactants. However, for precipitation reactions, my reactants are solids, and the concentration does not affect my equilibrium. So when we talk about KSP, it's going to be our products, the concentration of our products, raised to their coefficient. Okay? So we're going to talk about this term called molar solubility. And molar solubility tells me the number of moles of the solid or the precipitate that will dissolve in 1 liter of water. Okay? So moles per liter, molarity. How much of my solid is actually going to dissolve? The bigger my KSP, the more stuff is going to dissolve. The smaller my KSP, the less of these products I have, the less of my solid is going to dissolve. Okay? So here's the way I calculate molar solubility. I always have to have my equation. So I've got silver chloride, which I know breaks into Ag plus and Cl minus. I want to figure out how much of this can dissolve. Well, I know that if I have X moles of this, it's a 1-to-1 ratio between AgCl and Ag, so this will be X. It's a 1-to-1 ratio between AgCl and Cl, so that'll be X. Now when I look, I have my KSP value. KSP was 1.8 times 10 to the negative 10th. I know that's equal to the concentration of my products raised to their coefficient. Well, this is a 1. And then x to the 1, so x times x is x squared. If I wanted to solve for x, I'm going to take the square root of both sides. So 1.8 times 10 to the negative 10th. If I take the square root of that, I get x is equal to 1.34 times 10 to the negative 5th. This is going to be moles per liter. So 1.34 times 10 to the negative 5th moles per liter of AgCl can dissolve in solution. Okay? Now it's important that I always keep track of the equation, because the equation is going to seriously affect molar solubility. Here I've got lead 2 chloride. So again, I've got PbCl2. I want to know how much of that can dissolve. Well, it's a 1-to-1 ratio between Pb and Pb2+. So if x of this dissolves, I'll have x of that in solution. But it's a 1-to-2 ratio of PbCl2 to Cl. So that'll be 2x. If I look, KSP was 1.6 times 10 to the negative 5th. This is equal to x times 2x raised to its coefficient, so squared. When I do this, I have to square this first. So 2 squared is 4. X squared is x squared. So 4x squared. times x, so that'll be 4x cubed. If I divide both sides by 4, I get 4.0 times 10 to the negative 6th is equal to x cubed. Now when I take the cubed root, when I plug this into my calculator, what I'm going to want to do is I'm going to raise this to the power of 1/3. Now depending on the model of your calculator, it might be necessary to put that in parentheses, because otherwise it might raise it to the power of 1 and then take your answer and divide it by 3. So the older calculators, you're going to want to make sure your exponent is in parentheses. If I was taking the cubed root, it's 1/3. If I needed to take 1/4, if this is 4, 1/5 if this is 5, okay? So x is going to be equal to 0.159 moles per liter. So I know 0.159 moles per liter of PbCl2 can dissolve in water. Okay, that's its molar solubility. Now, if you notice, it's really important that I know the stoichiometry of the reaction. Okay, in the examples I just did, this was a 1-to-1 ratio, and my math was very simple. This was a 1-to-2, and so my math was a little bit more complex, and I needed to keep track of what was happening with exponents and things like that. So you want to know your stoichiometry, otherwise things get difficult. Okay? So equilibrium doesn't just apply to acid-base reactions, it also applies to precipitates as well, and we use our KSP values when precipitates form.